Thanks for the introduction. And first of all, I'd like to thank the organizers for the invitation, in particular, Haima, who is not here. Okay, today I will present some results on the construction of quantum many-fermion system on phase transitions in quantum many-fermion system. And the goal is to the ultimate goal is to to build a mathematical theory for metal superconductor phase transitions, but we are still far away from that. Okay, today's talk is, I will concentrate on a specific model called the honeycomb Hubbard model, but our methods are also suitable for other models in quantum many-body system, or quantum many-fermion system. Okay, so here is the plan of my talk. In the first part, I will briefly introduce the two-dimensional honeycomb Hubbard model and introduce present the main results. And the second part is the proof of the main results. The methods are fermionic cluster extensions and renormalization group analysis. We are concentrate on the inference behavior of the things. Okay, and in the third part, I will briefly talk about the Hubbard bond on another lattice called the 2D square lattice. And then we'll talk about some universalities. The last part is conclusions and perspective. Okay, I will start the first part. The Hubbard model is a toy model for describing interacting fermions on the lattice. But many people consider it as important, plays the same role as the Ising model in classical statistical physics. But we know much less about Hubbard model than the Ising model. Okay, the honeycomb model is a Hubbard model defined on the two-dimensional honeycomb lattice, which is a bipartite graph composed of two triangular lattices. One is noted by white dots and the other by black dots. By translation of the elementary vectors delta 1, delta 2, and delta 3, we obtain black dots from the white dots and vice versa. The fermions are living on the dots, on the black dots and the white dots. Since the fermions obey the rules of quantum mechanics, we will first construct the Hilbert space for the fermion system. Okay, we construct first the one-particle Hilbert space. Consider a torus on this lattice of size L, and we can easily construct the one-particle Hilbert space. Each function in this Hilbert space depends on three parameters. One is the lattice, the point on this torus. And the alpha, the variable alpha means the black dots or the white dots, and tau is the spin of the fermion. Okay. Then the Hilbert space for the fermion, for the many fermion space is also called the Fock space, which is defined as the tensor sum, the direct sum of the n-particle Hilbert spaces. And for any n, the n-particle Hilbert spaces is defined as the anti-symmetrization tensor product of the one-particle Hilbert space. Actually, you have already seen that on Monday. Okay, we just present some explicit example. Okay, for any say in the one-particle Hilbert space HL, we can construct the fermionic operators which obey satisfying the canonical anti-commutation relations like that. Okay. And here are the examples for the fermion for the operator A, which means the fermions on the white dots. Oh, sorry, they are typo. And we have the same canonical anti-commutation relations for the operators, fermionic operators B, which means fermions on the black dots. And these operators are bounded operators, and they form a system algebra, etc. Okay. So the operators A plus A minus also called the fermionic creation and annihilation operator, because they acting on vectors on the Fock space in this way. Okay, this you create from this one, and here you annihilate this one. So that's the reason why they call creation annihilation operator. And from this operator, we can define the thing called the fermionic fields, defined by this formula. The fermionic field here, the psi is the variables by position and the spin. And the fermionic operators are operator value distributions, essentially. Okay. And also obeys the canonical anti-commutation relation, of course. And this relation are given by this way. And the same relation for the operators P plus and B minus. Okay. Okay, with the fermionic fields, we can construct the many-body canonical Hamiltonian, which defines the Hubbard model. Okay, the Hubbard model, this Hamiltonian composed of 3 terms. The first term is the hopping term, and the T is called the hopping parameter. And the first term means that a fermion jumps from the white dots to the jump from the black dots to the white dots, and the second term means a fermion jumps from the white dots to the black dots. So each fermion jumps only to its nearest neighbor. And second term is a density term, and the coefficient mu is called the chemical potential. It controls the density of the fermions, average density of the fermions. And the last part is the interacting term. It's a density interaction, and this is the main feature of the Hubbard model. So when lambda equals to 0, then this only describes the hopping of the fermions on its nearest neighbor, and nothing non-trivial. But when lambda is non-zero, but when we turn on the interaction, then all fermions are correlated. So it's a non-trivial model. Non-trivial non-toy model. Okay, with this Hamiltonian, we can define the time evolution of the fermionic fields, defined in this way. It actually is the imaginary time evolution. The T, it is given by this one. Okay. Here, the x0 is defined on torus of minus beta to beta, and beta is the inverse of the temperature T. And then we can define the Gibbs state, which is a linear function on the space of fermionic operators. So it plays a role of probability measure. I mean, similar, but not exactly. And here the trace is taking me with respect to the vectors in the Fock space. And there's the normalization, which is called the partition function. Okay.
Is it the typo that your annihilator doesn't depend on X naught here, or
X naught?
I mean
Look at the evolution operator. Yes, just before this line. Yeah, this
X and this X are different.
Ah, okay. The X is different.
This
okay.
is a vector X, but well,
This is the full vector. Okay, good, excellent. Okay.
So it's not very explicit. But, okay. Then we can ask the interesting quantities of this model. These are, as we said, this plays a probability measure. The interesting quantities are the 2p, any 2p point Schwinkers functions, which are the moments of this measure. So here is an explicit expression for the two-point Schwinkers function. But we are interested in the 2p point Schwinkers function in the infinite volume limit, because after without taking L goes to infinity, the Hamiltonian is just bounded self-adjoint bounded operator, and the Hilbert space is just a finite dimensional Hilbert space. After choosing a suitable basis, you just have some matrix analysis of finite dimensional matrices, which is nothing non-trivial. But when L goes to infinity, the many-body Hamiltonian is unbounded operator, and everything becomes interesting. Okay. And the interesting quantities are the 2p point swing function, which are the moments of the given states, and also the connected swing functions, which are the cumulants of the measure, and also the self-energy function, which we shall define later. Okay, now we first look at the two-point swing functions without interaction, but taking the infinite volume limit. So it has a very explicit expression in the momentum space. Here this is a Fourier transform of for lambda equals to 0, it expressed as a Fourier transform of ck. And here the vector k is defined on a region. After taking the infinite volume limit, the k becomes continuous variables. They take values in a region called the first Brownian zone. But the k0 is a set of discrete variables depending on the temperature T. And they are also called the Matsubara frequencies by physicists. Okay. And the expression of ck0 is given by this. And here the k0 is this one, and omega k is called the dispersion relation. It characterizes the relation between the kinetic energy and the momentum of the fermions. And mu is the chemical potential. We said that for t is greater than 0, or for k0 greater than 0, then this free propagator is always well defined, so nothing non-trivial. But when t goes to 0, t equals to 0, then the free propagator, okay, this is the same expression. The ck0, k0 is singular on a site, on this side. This is a closed site in R2, and this site is called the Fermi surface. So the free propagator is singular. For t equals to 0, the free propagator is singular on this site, on the Fermi surface. The shape of the Fermi surface depends on the dispersion relation and the chemical potential mu. Since the lattice is given, the dispersion relation is given, so the shape of Fermi surface only depends on the value of mu. So there are some examples. When mu equals to 0, when mu equals to 0, then the Fermi surface is just a pair of points. They are degenerate. So this is, and they compose. They are just a pair of points. And when mu equals to 1, then the Fermi surface is a set of triangles. So here I just picture 2 of them, and the other can be obtained by translations. And here the k1 and k2 are the 2 Fermi points. And when mu is taking values between 0 and 1, then F0 is a set of convex curves surrounding the Fermi points, but are enclosed by the Fermi triangles. Okay. Yeah, this interesting. So now we go back to the interacting case for lambda non-vanishing. So the fundamental questions about this model is that the first question is that if this model is really well-defined model, can we make mathematical sense out of this model? Or is the partition function of the log of the partition function also called the free energy well-defined? And if this is true, then we can ask the analytic properties of the Schwinger functions. Are they all well-defined, and which kind of function are they? And we can, the third question is that, is the ground state of this model Fermi liquid? Also, Fermi liquid is an important notion in physics invented by, this theory is invented by Landau. Essentially, it describes the conducting electrons in the metal. And the mathematical theory, rigorous theory of Fermi liquid is defined, is given by Manfred Salmhofer, from Heidelberg. This is a mathematical definition of Fermi liquid. Let SC to beta be the Fourier transform of the. I mean, it's the kinetic Schwinger's function in the Fourier space, and the ground state of the system is said to be a Fermi liquid at temperature T. If first of all S2 beta is an analytic function of the coupling constant lambda. And the second requirement is that the Fourier transform of the self-energy function, which we mentioned before, is uniformly C2 in the extra moment k. Okay. So this is definition of the mathematical definition of the Fermi liquid. Up to now, there are not so many examples of Fermi liquid or non-Fermi liquid. Here are the example. The first example, I think, is given by Zhituo and Reversal. They studied the Jellium model, which is a manifold model defined on the continuum, but the Fermi surface is a set of circles, perfect circles. And they prove that there exists some critical temperature Tc such that the ground state, the equilibrium state is a Fermi liquid for T greater than Tc. And Tc depends on the coupling constant, and it is exponentially small in the coupling constant. And Beffato, Giuliani, and Mastropieto generalizes the work of Zhituo and Reversal. They still consider many Fermion system on the continuum, but the Fermi surface is central symmetric, not necessarily around the circle. And they prove that the ground state is Fermi liquid for T greater than some critical temperature Tc. They are not the same, but the scaling behavior are very similar. And also Feldman, Knöher, and Tobowitz studied many Fermion model with strictly asymmetric Fermi surface, and they prove the Fermi liquid behavior of that model for T goes to 0, which means that the system stays like metal and for all the temperature, and there's no phase transitions. And there are also models of non-Fermi liquid. Afshan, Magnier, and Reversal acting in a series of 3 papers, they prove that the Hubbard model on the square lattice at half filling, actually, which means that the Fermi surface is a set of perfect square. In that case, the ground state is not a Fermi liquid for T greater than some Tc, but the scaling behavior of this Tc and that Tc are very different. Yeah.
Is the Fermi liquid a theoretical object, or is it a real liquid?
Metal.
It's a metal, but
yeah,
does it happen in nature? Or
yeah, sure.
Yeah,
it's a very successful metal in condensed matter physics.
Yeah. Okay.
It's and this is the mathematician tries to make sense of it.
Yeah. Okay. Great.
Yeah, it's very successful. Yeah. This is physics. This happens in our nature. Okay. And also Afshan Magnier Reversal gives example of non-Fermi liquid in the Hubbard model square lattice, and then Beffato, Giuliani, and Mastropieto studied the same square Hubbard model, but with small chemical potential, which means that the Fermi surface is a set of convex curves, and they prove the Fermi liquid behavior in that model. Okay, so these are the other examples of Fermi liquid.
So I see 4 examples of TC. When you go close to the critical temperature, are the exponents, are the critical exponents the same, or are they completely different universality classes?
They are, the coefficients are slightly different, but very similar, but they show very similar behaviors. Yeah, the critical temperature, like exponential minus 1 over lambda. I mean, for the Fermi liquid case, and for the non-Fermi liquids, you replace lambda 1 over lambda by 1 over square root of lambda. So we will give explicit formula.
Thank you.
Okay, so these are essentially all the models of all the results of Fermi liquid and non-Fermi liquid. Okay, these are the models on. Now we go back to the honeycomb, to our honeycomb model. The first rigorous result of the honeycomb Hubbard model was given by Giuliani and Mastropietro in 2009, I think. They considered the interacting Hubbard model with chemical potential mu equals to 0. And this is their result. So there exists a positive constant U such that the pressure function and kinetic shrink, 2-point shrink functions are analytic function of lambda for beta goes to infinity, for lambda smaller than U. I mean, for all lambda smaller than U, which means that this took as long as lambda is smaller than U, then the 2-point shrink function is an analytic function of lambda, which means that there's no phase transitions in this model. This is also called the honeycomb, the graphene model. Okay, very well known in physics. Okay, but the second rigorous result is given by Vincent Riverson and myself, and we consider the case of interacting honeycomb Hubbard model, but the chemical potential is equal to 1. In this case, as you remember, the Fermi surface is a set of perfect triangles, and we prove that there is a constant, positive constant beta c, such that for all beta smaller than beta c, the pressure and the kinetic shrink functions are kinetic functions of the Copley constant lambda. I mean, the analytic region of lambda is given by this formula. And for if you fix a sufficiently small lambda, then you can obtain the critical temperature. The critical temperature is given by this one. Okay. And this is the first result. And then we prove that the self-energy function is just one C1 epsilon, if you like. The first derivative is and sigma is C1 uniform in K, but the second derivative is not uniformly bounded for T goes to infinity for T goes to 0. Which means that it doesn't satisfy the criteria of Salmhofer, and means that the ground state is not a Fermi liquid. Okay, this is our result. Okay, then I will briefly sketch the proof. The proof will be using fermionic cluster expansions and renormalization group analysis. So in order to give you the proof, it is more convenient to express the shrink functions in terms of the Grassmann integrals, which we have already seen on Monday. So I will recall again the Grassmann algebras. So, but here is an explicit example. Explicit construction. The Grassmann algebra is an associative non-commutative nilpotent algebra generated by the Grassmann variables, and the Grassmann variables are defined on that, and it's defined on here. The K0 is a set of sequences, and the K, the vector K, is in the first Brillouin zone defined before. And they satisfy this any commutation relation. The square of any Grassmann variable is 0. And we can define the Grassmann differentiation and the Grassmann integral. They are essentially the same. And you can find a model for the Grassmann algebra, which is the exterior algebra in differential geometry. And with this Grassmann variables, you can define a Grassmann Gaussian measure with covariance CK in this way. And here the inverse is normalization constant. And for any two Grassmann variables, you find this rule. So the covariance of the Grassmann variables is really the CK. And that's why we introduce the Grassmann variable. We have a better representation for the free propagators, and it's easier to perform the multi-square analysis. Okay, we can also define the Grassmann fields, which is formulate the Fourier transform of the Grassmann variables, and of course it is also a Grassmann variable. Okay, and then we can express, we can rewrite the interaction term like that, and you can define the normalized Grassmann measure, the interacting measure like that. It is not a Gaussian measure, of course, and the ZL is the partition function. Essentially, we rewrite the formula in the operator algebras in as the Grassmann integrals. Okay, the shrink functions are the moments of the Grassmann variables. Okay. Then we can define a few quantities. We can define we can call J plus J minus be two additional Grassmann variables called also the source term. Then with the addition of the source term, the partition function is a moment generating function. And taking log of the moment generating function, you obtain the cumulant generating function, And after performing the Laurent transform, you obtain the generating function for the self-energy. Okay, so self-energy is we introduced the much earlier, but it's most easily defined in terms of Grassmann integrals. Okay, so these are the quantities. Then due to the presence of the non-Gaussian term, it is not we can't obtain the lambda directly. So we have to consider the quatic term as a perturbation term, and the naive perturbation is that we perform Taylor expansions of this term, and after performing the Grassmann integrals, we obtain a very big determinant. Here we change the summation and integration. Of course, this is allowed only when this is finite by Fubini, but we can assume that this is finite, and we will see the problem of the naive perturbation theory. Okay, and then after fully expanding this to be determinant, you have the perturbation series, and as this introduced by Razon, Guho, Vincent, and Thomas, the perturbation series is not convergent because there are too many terms, because the Fermi graphs proliferate too fast. You can also see it in a more direct way because this is a 2n times 2n dimensional determinant. After fully expanding this determinant, you have 2n factorial terms, but you have only n factorial term in the denominator, so the result is still n factorial. So and this perturbation theory is not it's not convergent. Okay, so this is the problem of naive perturbation expansion, and we shouldn't use it. Okay, so this problem, the solution is that we shall use some Fourier formula to partially expand the perturbation term. Actually, as we said, there are too many perturbation terms, and we can label each of the perturbation terms by graphs called the Feynman graph. So the problem is that there are too many Feynman graphs. But instead, we should find a better expansion. We don't expand according to the Feynman graph, but expand according to the spanning trees or spanning forests of the Feynman graphs. And there are much less forests or trees than graphs. Okay, so in other words, we can partially expand the determinant so that only the perturbation terms labeled by forest or trees appear. And we shall bound the remainder term by other ways. Okay. Okay. This is the idea of the fermionic of the forest formula or tree formula, which has already introduced by Thomas. So I will be very sketch. So you can formulate for any given Feynman graph G, I mean a big Feynman graph, and you can consider the set of spanning trees of this graph, and you can define a probability measure on the set of on the set of trees. And then using this probability measure W, you can rewrite the amplitude of the Feynman graph in this way. And formally, by this combination, you can rewrite the sum over graphs as sum over trees. So if the amplitude is finite, then the sum over tree, I mean the canality of trees is much less than the canality of the set of graphs. Okay, this is an explicit formula for calculating the probability measure of a given tree in the probability of a tree in a given graph. This has already been introduced already in the talk of Razvan-Guho. So the rule is like that. For any tree, for any tree lines, we shall associate a parameter W. And for any lines not in the tree but in the graph, which also called the loop lines, we shall assign a weakening parameter XT. It is defined like that. Since this graph is okay. For any loop line, it must have two vertices V and V prime, and this V and the V prime must be connected by a tree line, by a path of the tree lines in the graph, and this weakening parameter is defined by the infimum of the tree lines. Here are typos because here for G a kinetic graph, then all the we only have spanning trees, so this doesn't happen. So I forgot to change. So and the interest reader could also look at this paper for some examples of WGT. Okay, the canonical way of defining ways of the spanning trees in a graph is the BK AR forest formula, which has been introduced before. Okay, this is the first question. There are too many terms in the expansion, then we shall use the Fourier expansion. We shall partially expand the determinant. And the second term is that, as we remember, the free propagator is singular on the Fermi surfaces. And using the perturbation method, we will express all the interacting Schwing function in terms of the free propagator. So we will have some iterated integration with singular integration kernel. This is a second problem. So first of all, we should avoid all the 2 times integral. And also for the L1 norm of HCK, we should perform the integration step by step and try to get rid of all the possible singular terms. Okay, and this is performed by multi-scale analysis. We shall divide the integration domain around the Fermi surface into a set of annulars according to the distance with respect to the Fermi surface. And this is we introduce a convex box function, and we use partition of unity, and then we can define free propagators supported on the annulars. But this is still, this is a step. But this is still not enough to get the optimal decay behavior for the propagator due to the mismatch of the propagation in the momentum space and the position space. So we should further decompose the support of the propagator. So we introduce sectors. Okay, this is the set. Okay, well, we introduce another set of partition unity, and then we decompose each annulus in terms of sectors, a little bit more complicated. And here the sectors is a rectangle with size gamma minus SA times gamma minus SB, and the SA SB are integers and should satisfy these constraints.
What determines J max?
J max is log T. Okay, we only with the introduction of sectors, can the free propagators have the desired decay behavior, and we have the desired bounds for the propagators. This is the L infinity norm and the L1 norm, and they are the desired optimal norm. So combining the forest formula with the multi-scale analysis, the resulting formula is slightly more complicated than the BKR forest formula. Actually, it is called the BKR jungle formula because for each tree, for each line in the forest, each line is also labeled by some scaling integers. So it's the BKR jungle called the BKR jungle formula. And this formula is also obtained in the same paper by Abdel Salam and Reversal. Okay, after performing the BKR jungle formula to the two-point Schwing functions, we get this a complicated expression for the two-point Schwing functions. And here we sum over all the jungles, and all the amplitudes are organized according to another tree structure called the Galavati-Nicola tree. But here we will not explain the Galavati-Nicola tree. I have some. Here, Galavati-Nicola tree essentially tells you how the vertices are organized into a kinetic amplitude. And they are going from the high scaled to the low scales. And this is the French version. This is the Italian version of the Galavati-Nicola tree. Here, R is another scale parameter of this Galavati. Okay, and then there's a third difficulty. The problem due to the presence of many body interaction, the dispersion relations receive some quantum corrections, so that the singularities for the propagator is not fixed. It is moving at a different scale. So this is a problem of moving Fermi surface, and this could cause a lot of divergences in the perturbation series. And our way of treating this problem is to adding some counterterms to the original Hubbard model, such that the counterterm could cancel the term due to the quantum corrections. This tadpole and this quantum, the local quantum corrections and non-local quantum corrections. And here this counterterm cancels the self-energy, and this term cancels the determinative. And this cancellation is carried out in the multi-scale representation using renormalization theory, and they are performing according to the Galavati-Nicola trees from the leaves at a higher, from vertices at a higher scale to the vertices at a lower scale. Okay, here's some examples for, here's the constellation of local term and the constellation of the non-local term, and with a remainder which is bounded by a very small parameter. Okay, so then we are ready to obtain the analyticity of the two-point Schwenk function. We have the desired L1 norm and L infinity norm for the free propagators supported on sectors, and we performed renormalization for the two-point functions to get better bound. And as we said, we performed the Fourier formula to partially expand the determinant, and for the rest. We shall use the Graham-Adama inequality to bound the rest determinant by this one. And since we have introduced a lot of sectors, we have to carefully sum over the sector indices by taking care of the conservation of momentum. And this is called the sector counting lemma, first introduced by Feldman, Mann-Riversdorf, and Popovich. And here we mainly use the sector counting lemma approved by Riversdorf, and later I proved a sector counting lemma for a more general Fermi surface and with less regularity properties. Okay, and the summing over spanning trees is bounded by n factorial, which could cancel the n factorial in the denominator, and the result is summable. So we can prove that the perturbation series is convergent in this region. I mean, after all this. Okay, for the as you remember, we to prove whether this is Fermi liquid or not, we should consider also the regularity of the self-energy. But the self-energy is in graph representation. The kinetic Schwenk functions are given by kinetic graphs, but the self-energy are given by the two kinetic graphs, also called the one particle irreducible graph, which means that after deleting one line, you could not disconnect the graph. So again, the idea of generating this two kinetic graph is still to partially expand the remaining determinant such that one particular irreducible graph can be generated in some channel. We don't fully expand the determinant, but only partially expand the determinant, so that this one particular reducibility can be achieved. But still, there are many things we don't expand, and we bound all these terms by Graham-Adama inequality. In this way, actually, this expansion is called the multi-arc expansion. I think first invented by Yagonis and Mannian, I think. And then, but the first application of this formula in condensed matter physics is given by Zhituo and Riversdorf. Okay. Then we can establish after have converted expression for the perturbation series of the self-energy, we can estimate the regularities of the lower and upper bounds for the self-energy, and the lower and upper bounds for the second derivatives of the first and second derivatives of the self-energy. And we prove that a second derivative is not uniform bounded for t equals to 0. Okay, then we talk about the Hubbard bound on the square lattice, which I introduced before. On the Hubbard bound with square lattice, when mu is small, the Benfato and Giuliani must fail to prove that the ground state is a Fermi liquid. The critical temperature is given by this one. And as you remember, after Mannian also proved that for mu large, mu equals to 2, the ground state is not a Fermi liquid. I mean, for this critical temperature, they have different scaling behavior. So there's a crossover of the different states. So I consider, by slightly moving the slightly changing the chemical potential, there should be, some crossover, and I would like to study this behavior. And we consider that the chemical potential mu equals to 2 minus mu 0, in which mu is much smaller than 1, but fixed. And we prove that the critical temperature is given by this one. If mu 0 is greater than the critical temperature, and TC equals to this one, which is essentially the same as this one for mu0 goes to 0. Okay, so this shows the behaviors of the Hubbard model on the square lattice is very similar to the Hubbard model on the honeycomb lattice. They have very similar scaling behaviors. Okay, so conclusion, we have provided rigorous proof that the ground state of the honeycomb Hubbard model is not Fermi liquid, and we have established the non-perturbative phase transition critical temperature TC, and then we should ask what will happen for mu between 0 and 1. Then the Fermi surface is set of convex curve, and this should be done. And another interesting thing is to add some quasi-periodic potentials on the model, and to see if there could be uncertain localizations or many-body uncertain localizations. Okay, so these are the reference of my talk. Okay, thanks a lot.
Thank you.
Oh.